Have you ever wondered if the complex, knotted shapes in the universe are hiding a flat, infinitely simple version of themselves? To find out, we look to algebraic topology, a framework that translates tangled geometry into clean, trackable rules. Think about taking an infinitely long string and wrapping it over and over around a single circular ring. That string is what we call a covering space of the circle. Our objective is to push that unwrapping process to its limit. We want to find the master blueprint for any given shape, a unrolled, flattened out version. But before we can locate that master blueprint, we have to prove when two distinct wrappings are actually the exact same shape in disguise. For this, we turn to the definitive text, James Munkres' Topology. Let's examine sections 79 and 80. Our primary tool is the fundamental group, or pi1. This is the algebraic device that measures and counts the topological holes within a space. We are going to use pi1 to construct a strict dictionary. One side contains physical topological spaces, and the other contains purely algebraic subgroups. If we map the physical geometry to the algebra, we can solve complex, multidimensional problems using standard equations. If we have two different covering spaces, we'll call their maps P and P', wrapping around the same base space, B. How do we verify if they are doing the same job? Munkres gives the formal definition in section 79. This diagram shows covering spaces E and E', pointing to base space B. For equivalence, homeomorphism H must map the top space onto the other, so their base projections are identical. When that condition is met, the two covering spaces are the same geometric object. They might carry different labels, but they fold over the base space in the precise same manner. The challenge is proving this homeomorphism exists without having to map out every single point of infinite spaces by hand. This brings us to the engine of the theory, Munkres lemma 79.1, the general lifting lemma. In figure 79.1, the lemma works by taking a path in the base space, labeled alpha, and trying to lift it into the covering space E. It proves lifting is only possible if the starting space's fundamental group is contained within the cover's fundamental group. That rule gives us theorem 79.2. As shown in figure 79.2, two covering maps are equivalent if and only if their fundamental group images are exactly equal. This moves the proof past the geometry. Testing for topological identitality is now a check of whether two algebraic subgroups match. Let's apply this equivalence theorem to the simplest space with a hole, the circle. The fundamental group of a circle is isomorphic to the integers, denoted by z. That integer represents the number of times a loop winding around the hole. The algebraic subgroups of the integers are simply multiples of an integer n, 1z, 2z, 3z. Every valid covering space corresponds exclusively to one of these subgroups. 2z represents a double wrapping, 3z a triple wrapping, and so on. This grounds our abstract dictionary in a tangible space that we can easily picture. Now, consider what happens if we push the unwrapping process to its limit. In our dictionary, that corresponds to the trivial subgroup containing only 0. Section 80 defines this limit as the universal covering space. This cover is simply connected, meaning its fundamental group is empty of holes. Figure 53.4 shows this for a torus. The universal cover is an infinite, flat, two-dimensional plane, wrapping infinitely over the surface of the donut shape. Why does this specific flat plane earn the title of universal among all other possible wrappings? Theorem 80.3 provides the answer. Because space E contains no holes, it covers the base object B and every other intermediate covering space Y. The simply connected cover is the definitive master blueprint because it contains the unrolled structure of all other potential covers within it. While this master blueprint is powerful, not every shape in the universe possesses one. Munkres introduces a counterexample, the infinite earring. It consists of infinite circles shrinking down to a single point at the origin. Because they converge there, you find non-trivial loops tightly packed into every microscopic neighborhood. those loops can never be isolated or flattened. Therefore, the infinite earring can never be fully unwrapped into a simply connected space. For a universal cover to exist, a space must be semi-locally simply connected. Even unwrapping infinity has strict boundaries. We now have a bijective dictionary mapping the vertical hierarchy of topological covers to corresponding nested algebraic subgroups. The fundamental group dictates their geometric reality. Anchoring the top of the stack is the universal cover, corresponding to the foundational trivial subgroup. By translating complex spaces into groups, algebraic topology turns the task of visualizing infinite folds into a solvable equation. If you want more deep dives into standard mathematical texts like Munkres, remember to like, subscribe, and leave a comment. The hardest concepts in graduate mathematics become manageable once you know how to build the right dictionary. Thanks for watching.